Hello class. Today's lecture is going to be on dynamics and Newton's laws. We're going to look at all three Newton's laws, talk a little bit about the history of some of them, also discuss a little bit of mass and weight, the difference between those concepts today. So let's get started. If we look at our note sheet, again, up to this point we've studied the motion of objects. So we've talked about what's called kinematics. We did some kinematics problems and then also went into some free fall problems with some projectiles as well. And now we're going to start learning why that motion exists. And that study is called dynamics. So let's look at why. First of all, we need to understand the concept of Newton's laws. So the first of Newton's laws states that an object continues in a state of rest or motion in a straight line at a constant speed unless it's compelled to change by some external force acting upon it. So what this is saying is that all objects will continue doing what they're doing until we exert external forces on them. For example, if I were to roll a marble across the table, it's going to continue to roll forever if that were a frictionless surface. If I put my hand in front of it and exert a force on it, I can get it to stop or change direction. And again, if I have an object sitting on the table, like a mouse, it's going to continue to stay at rest until I give it an external force to get it to accelerate or change direction. A couple concepts here. First is inertia. Inertia is the resistance an object has to a change in its state of motion. Inertia is a measure of the object's mass. So the greater the mass of an object, the more inertia it has. And think of it this way. If we were watching the Colts this afternoon, what kind of person do you want as an offensive lineman? Someone with a little bit of mass who is easy to change his state of motion, or someone with a lot of mass so it's harder to change their motion? And you would say that Andrew Luck would want someone with a larger mass so that they have more inertia, which means they have a large resistance to a change in motion, so that way they can stand there and it takes a lot of force to get them to start moving. The SI unit of mass is the kilogram, and Galileo was one of the first gentlemen to discover the idea of inertia, and he was kind of shunned because of his ideas. They put him on house arrest. They kind of thought he was crazy because all of his contemporaries at the time disagreed with him. But actually Newton kind of confirmed what he had said, that Galileo was correct. So the difference between mass and weight, because a lot of times here in the United States we use those two terms interchangeably, and really they're not. Mass is a measure of the amount of matter that an object contains, and weight is the measure of the force of gravity acting on the object. So the first point there says that it's independent of location, mass is. So if I take a 1 kilogram object from here to the moon, it still contains the same amount of matter. So mass is measuring that. It would not change from here to the moon. Weight is location dependent. So if I take a 1 kilogram object, it's going to weigh less on the moon because the gravitational force on the moon is less. And then finally, mass is not volume. There's sometimes some confusion there. Volume is how much space that an object occupies. So I'm taking up a volume of space. If it has a large mass, it might not have a large volume, so it could be a very dense object. So if I look at this, if I had a mass that was very big and a volume that was very small, that would mean it would have a large density. Then we have a little factor label here. Good to get back into this a little bit. If I want to find the mass of 2.0 gallons of water, a unit of mass, again, could be kilograms, could be grams. We're going to convert to kilograms here because that's our SI unit that we want to get to. And we're starting with 2.0 gallons of water. And it gives us a conversion factor here. This is a volume, gallons is a volume, and mass is, kilograms is a mass. So we need a conversion factor that relates mass and volume, and that would be the density of water. So I need to get gallons to milliliters in order to use this. I'll then do a milliliter to gram conversion and then a gram to kilogram. So let's kind of look through the steps there. Again, if you want to pause the video, try to do this factor label based on what you know on your conversions, and then come back and you can see the answer. Okay, here's our answer. Again, we can see that we've gone from gallons to quarts, quarts to liters, liters to milliliters. Then here's our density conversion, where we're going from milliliters to grams. Again, using this right here, 1.0 gram per milliliter, and then grams to kilograms to get us that particular answer. Again, you multiply the top numbers, divide by all the bottom numbers. You can quickly see that the 1,000 and 1,000 cancel. So really you just have 4 times 2 divided by 1.06, and that's good to 2 digits. So that's our answer there. Here, 1 kilogram is equal to 9.80 newtons. So this is the weight of 1 kilogram on Earth. And here's how we find it. We use this equation here. The weight of an object is mass times its gravitational acceleration, and little g on Earth is that. So what would the weight of a 5 kilogram box be? Well, 5 times that many newtons, or if we show our work, again, weight is equal to mass times little g. Weight would then be equal to 5.00 kilograms times 9.80 meters per second squared. So our weight would be 49.0 newtons. And then what if we were on Saturn? Well, again, Saturn, a larger planet, has more mass, therefore the gravitational acceleration is greater. It's 11 meters per second squared. So if I'm on that planet, so this would be the weight on Saturn, it would be mass times gravitational acceleration on Saturn. So the weight on Saturn would be 5.00 kilograms. Again, that stays constant. And then our little g is 11 meters per second squared. And here I'd get 55 newtons. So again, larger gravitational acceleration, we get a larger weight. However, our mass stays constant. That's Newton's first law. The law of inertia is typically what it's known as, and we should have that memorized now. Newton's second law deals with the acceleration of objects and how certain objects accelerate more or less depending on the force applied and their mass. So let's take a look at that. Acceleration produced by a net force on an object is directly proportional to the magnitude, basically the size of the net force, and inversely proportional to the mass. And this should make sense. If I look at this equation here, if I increase the force, the net force on an object, what should happen? Should it accelerate more or less? Well, if F net goes up, acceleration has to go up. And inversely, if the mass goes up, so if I get a bigger mass, am I going to be able to make it accelerate as much with the same force? And that's false. So if you take the difference between a golf ball and a bowling ball, and I throw them as hard as I can each, I have the same force acting on them when I throw them, but because the mass of the golf ball is significantly smaller, it's going to have a greater acceleration, so it's going to be able to be thrown faster than the bowling ball. It says when a net force, what is a net force? A net force is basically it's the sum of all the forces acting on an object. So we look at the sum of the forces in the direction of motion, and we subtract the sum of the forces that oppose motion. That's going to give us a net force. So basically, if I want to know what's the net, what is your net paycheck, you would take all the money that goes that you get from your job minus all the taxes that were taken out, and that would be the net result of your paycheck. That kind of be an example for you. So let's look at this next concept. It says when a net force acting on an object is 0, there is no acceleration. So if I had a 0 for a net force, that would make the acceleration 0. So there's no acceleration. Which means that an object does what? It moves at a constant velocity. So let's look at our first example here. We have a force of 30 newtons acting on a box as it's pushed across the floor. I always draw pictures. I recommend that you draw pictures for everything. They don't have to be great. I'm not an artist either. So there's my box. I'm going to put 30 newtons acting on it. So I'm going to draw an arrow for a force vector, and I'm going to put 30.0 newtons acting on it. Now if I have friction that's 10 newtons that opposes the motion, which direction would that be going if it's opposing motion? Well, it should be going in the opposite direction. So I'm going to put another force vector here, and it's going to be 10.0 newtons. That would be my force of friction. It says determine the acceleration of the 10 kilogram box. So we know that this is 10.0 kilograms is its mass, and we want the acceleration. Acceleration is net force over the mass. Well, we know the mass. Do we know the net force yet? No, we don't. So we're going to have to determine that. So we're going to do a separate equation. And the net force equals the forces in the direction of motion, which, again, if we're assuming that it's going this direction, so it's the forces going this way, minus the forces that are opposing motion, which are going this way. So net force would be 30.0 newtons minus 10.0 newtons. I get 20 newtons there. Again, addition rule, looking for tenths. Tenths, answer as tenths, carry an extra. Now we can plug it into here. And again, I get a unit or a value of 2.00 meters per second squared. And how did I get this unit? Well, a newton, if you remember earlier, was we took mass, which is measured in kilograms, times gravitational acceleration, which is meters per second squared. So a newton is a kilogram meter per second squared. So if I have that value and I divide by kilograms, so if I divide this value here by kilograms, you can see that kilograms cancel, and what are you left with? Meter per second squared, which is our unit for acceleration there. Alright, let's look at the back sheet, or the second side of this. Let's look at our next example. It says an object is pulled along a table by 50 newtons of force in the direction of motion. If the object is moving with a constant velocity, what is the acceleration? So right away we should be thinking, okay, if I have an object that's moving with a constant velocity along the table, there has to be something true about the forces acting on it. So if this were my object and I'm pushing it with a constant velocity, the acceleration, again, if it's constant velocity, help me out. Good. It's 0 meters per second squared. It's not accelerating. So what is the value of the frictional force? Well, let's diagram it. If I put a 50 Newton force on it, and the acceleration is 0, what does the acceleration tell me about the net force? Well, if I have 0 acceleration, it means the net force is 0. And if the net force is 0, that means all the sum of the vectors acting on it are 0. So if I have friction that's opposing motion, and I have a 50 Newton that's forward, how many newtons is going to be pushing against it? Good. I'm going to need a 50 Newton force acting against the force that I'm pushing with, so that they cancel because they're in opposite directions, same magnitude, so their net force is 0, and if I have a net force of 0, that means my acceleration is 0. So it says, what is the value of the frictional force? It would be 50 newtons. And again, friction is opposing motion always, so the direction would be in the opposite direction of motion. The next video will explain terminal velocity and Newton's third law, so again, that will be part 2 of this. Thanks.